In the last section, we talked about the idea of this concept of the derivative. That was, we were able to create a function or a formula that would tell us the slope of a tangent line at really any point on a curve. And this is summarized here in this definition that we established in the last section. We said that the derivative of a function f would first be denoted by this set of notation, f with a little tick mark of x, which we read as f prime of x. And we said that this was going to be representative of this big scary limit, which you may recall, if I ignore this limit portion right here in the front, and I just look at what I have here, this is a formula that calculates the slope of a secant line. And the goal of the limit was to say that I want to go ahead and make the gap that exists between my two x values move to 0 gap. That's how this gives us the slope of a tangent line. So this is a really important idea that allowed us again to create a formula for slopes of really any tangent line on the entire graph of a function. So let's take a look and summarize this down here at example number 1. If f of x is, say, the square root function, then can I find the derivative of f? And then I'm going to go ahead and state the domain of the function f as well as its derivative, which would be denoted f prime. Okay, so I'm going to go here and start showing how exactly we would calculate this. So what we would say is that using the definition, that is the one in the box up above, we calculate, and we would start calculating f prime of x. So notice again, right now, x is not going to be filled in yet with a specific number. We're going to keep x in here as kind of a placeholder. And so when we leave things again in this general format, it's like we're trying to find the slope of the tangent line at any point on the graph. It's like an undetermined point that we can choose later. So we know that we have to set up this big scary limit and evaluate it. Now again, we can't plug in 0 right away because that would force us to divide by 0, and that's no good. So instead, we'll go ahead and start to see if we might be able to simplify some things down. Now that will, of course, require that we write out the top in detail. Notice if I go to the function f and I plug in x plus h wherever I see an x, I'm going to get something like this. And then if I have minus just f of x itself, I'm going to have just minus that square root x. Now, a good way to simplify some stuff here, if I happen to have some square roots involved, might be, again, to multiply by a conjugate. So maybe x plus h under the radical plus square root x, and I'll multiply by the same thing to the bottom. Now, if I do this, and I think about what I'm going to be left with, on the bottom, I'm going to have a whole bunch of stuff left over. So I'm going to have my h, and then kind of multiplied by the sum of these two radicals. In the numerator, though, remember I created a difference of squares, or a factored difference of squares, by multiplying by the conjugate. And so when I multiply this out, I know it's going to be the first quantity squared, so the square root of x plus h. When squared, we'll just create that x plus h. And then I'm going to subtract my square root of x squared, which is just going to be x. Now, of course, fortunately here, I'm going to have that my x's are going to simplify out here. Ooh, and actually, I'm then going to be left with an h over an h. And so my h's are actually going to be able to cancel once those x's are gone as well. And so in total, I'm going to end up with here a limit as h approaches 0 of 1 over square root of x plus h plus the square root of x. Now I can see that if I'm going to do a direct substitution, because again I'm working with a nice continuous function here, assuming the denominator doesn't turn into 0, then as long as my denominator doesn't turn into 0 and I don't end up with like a negative underneath one of these radicals, I'm good to go. So I'm going to go ahead and directly substitute, and that's going to give me the square root of x plus 0 plus another square root of x. This is, of course, just going to be the square root of x plus another square root of x in the denominator, which we could write as, well, that is now 2 square roots of x that we have down there. So what we actually came up with is, again, a nice formula that is the derivative, the slope of the tangent line. Remember, every time you hear that word derivative, you want to automatically translate that to slope of a tangent line. The slope of a tangent line at any point on this graph is given by the following formula. So if I was to go ahead and think about taking a look at the graph of the square root of x, again, it's one of our graphs to know, so I should have an idea of what this looks like, but it looks something like this. So here is f of x equals the square root of x. This formula will tell me the slope of the tangent line at any particular point. So notice what's so great about this is that if I said, well, maybe I want to find the slope of the tangent line over here at the value of 1, right? And I could imagine like a little tangent line formed. What's the slope of that tangent line? Can I find it? Well, sure, I would just plug 1 in for x, indicating I drew a tangent line above 1, and so the slope of that line there would be 1/2. I could keep going, right? I could say like, all right, well, what if I wanted to draw a tangent line over here at maybe, say, the value of 4? Hey, well, that's okay. This tangent line is not as steep as before. It's a little bit flatter, but easy to find the slope there. I just say I'm going to plug 4 in for x, and that's going to give me 1/4 as a grand total. So I can see again that the purpose of having this formula is that I can grab a lot of values really, really quickly. Now, another thing that's going to be important to note here is the domain of the original function and the domain of its derivative. So let's go ahead and actually record that here. I'll note that the domain of the function f of x itself, that domain was actually going to be, well, let's see. I just really can't plug in negative numbers there, right? Negative numbers are bad to plug inside of square roots if I'm not interested in working with complex numbers. So 0's okay, and it's actually perfectly fine to go as high as I want into the positives. However, when I look at the domain of f prime of x, that is, I take a look at the domain of the derivative, again, I recognize that negatives are really, really bad. But this time, I'll also notice that plugging in 0 is really bad. Because if I plug in 0 for x, I end up with 0 total in the denominator. And that is something that I can't do. I can't divide by 0. So I can go from 0 to infinity, but I can't include the value of 0. So what we see here is that the domain of the derivative may actually be different than the domain of f of x. That is, the numbers we're allowed to plug into the derivative may not necessarily always be exactly the same numbers that we're allowed to plug into the original function. Now, of course, here it's pretty self-explanatory to kind of see why this might be the case and what the issue is down here at 0. To help with this, I'm going to go ahead and take a look here at a little applet to try to help show that on my square root function, I can get a lot of different tangent lines. Again, if I keep changing the value of my input, which right now I'm calling a, I can see that I get different tangent lines of different slopes. But you can start to see the trend in what happens if I start to move a towards 0. What seems to happen with the slope of this tangent line? Well, notice the slope's getting really, really steep, and by the time I get like all the way to 0, notice where would the line technically be headed? It looks like it's headed for like a perfectly vertical tangent line. And actually, that's exactly what's happening here in the picture. I have this perfectly vertical tangent line that is going to form right here at 0, and the slope of a vertical tangent line is undefined, which is actually exactly what we get when we plug 0 in here as well. So it's important to kind of see again how our derivative is being used and what it's good for. Now, one final thing before we end this video is that some of you may be aware of some derivative shortcuts or formulas that you could use to quickly calculate a derivative without going through this big long limit. This is sometimes a big problem and a big hindrance to people learning calculus. If you've taken calculus before, some of your knowledge that you may have previously acquired may get in the way of understanding some of the things that we're going to be talking about. So please be very careful to only use things that we have talked about in this class. So it's important that if you're ever asked to find the derivative of a function, right now, the only way we can do that is to actually use our big scary limit thing. And if you're asked specifically later on to use the definition of the derivative, you need to complete the problem as we did in the example up above. Okay? So please keep that in mind. If you ever have questions, though, about if you're using something that's appropriate or not appropriate, that's never a problem to just ask me. I'm more than happy to respond to that via email or in office hours and talk with you about, when new content's going to be coming up, when those ideas may be valid to use in our class.